squared. So that is your assignment. That is your assignment. So pi squared you will get exactly pk prime. How will you do? You will have to go with the expression for your pi. So earlier we went the expression for your phi. Pi is nothing but that. So we know already pi. Earlier see pi of x is given by this. We will have to use this expression. We will have to use this expression. So here and use the same calculation. You will get exactly instead of qk you will get pk. So pk dagger. So that is your assignment. So second two terms are over now. Two terms are over. This term is over and this term also is over. Now we are going to go with del phi. We are going to deal with del phi. So we know already phi of x is given by this. Del phi is nothing but partial d by dx. We are going to differentiate with respect to x. So you are going to differentiate this with respect to x, that will give you qk e power ikx. So your del phi whole square, again del phi whole square will give you del phi dagger del phi. Okay, similar thing. So you have del phi which is nothing but del phi is given by this, del phi dagger is given by this. You will have to replace its own complex conjugate. So that will give you minus ik qk prime e power, here it is plus, so here it is minus. As usual same argument, you will get, you just pull ik, you have ik multiplied by minus ik. So minus is there, you have I into I squared minus 1, so plus 1, k into k squared, qk and qk prime is here. The remaining can be written as del k minus k prime. So we have already seen this one. Okay, similar argument. This will become 1 when k prime equals minus k prime. So k prime should be replaced with minus k prime, and we know that q minus k can be written as qk dagger. So you have qk dagger with k square. So we have also found out now del square. Okay, so three terms are over now. So we can substitute. Okay, we can substitute in Hamiltonian equation. So we have substituted. So we have already calculated for pi squared, del phi squared, pi squared in terms of qk and pk. So in terms of qk and pk. So we have substituted here. And you know k squared plus m squared, just take common out, that will give you qk dagger. As omega k squared equals k squared plus m squared. K stands for wave vector. In linear harmonic oscillator, K stands for force constant. Omega equals root of K by M. Can you remember? We should not confuse with that. Omega equals root of K by M. Here it is omega K squared equals K squared plus M squared. They are all in K space, momentum space. They are all in real space. Okay. So now we have we can replace k square plus m squared as omega squared. So your complete expression is given by this in terms of pk and qk. Now in linear harmonic oscillator, we have replaced with x and p with the corresponding operators, creation operators and annihilation operators. Similarly, we are going to replace this as with creation operator and annihilation operators. There also we have done the same procedure. Procedure is the same. Results also will be the same. That is for the particle and this is for the photon. Okay. So qk is replaced with this expression. This is for qk in terms of creation annihilation operator, and this is for pk with this expression. Thus the Hamiltonian for the scalar field has become an infinite sum of various frequency modes of normal harmonic oscillators. So we are talking about here harmonic oscillators. So in the year 1900, the harmonic oscillator term was introduced by Max Planck, first time. Harmonic oscillator. When he was doing some when he was calculating the Planck's idea about black body radiation, and immediately he said that the energy absorption, the energy released, which is nothing but your oscillators. It comes out through oscillators. Okay, at the time he predicted, he introduced the term harmonic oscillator. So after 30 years, scientists proved this one. Okay, scientists proved. Okay, harmonic oscillators. Now we are going to introduce the expression for operators. So they are all creation operator and annihilation operators. So this is your annihilation operator. This is your creation operator. This annihilates with a positive energy. This creates with a negative energy. Very important one. Okay, see AK, here it is A minus K, dagger is there. So as I said, this will create a particle with a positive energy. No, this will annihilate with a positive energy. This will create with a negative energy for the antiparticle. Is it okay? So now, and this is your expression for your H, Hamiltonian density. This is for Hamiltonian density. Now we are going to substitute for pk. See pk. We are going to substitute for qk. We are going to substitute now. Okay, pk is given by this. Pk dagger is given by this. I repeat, pk is given by this. Pk dagger, just you have to take the complex conjugate. This will become minus I. See minus I. Of course, summation over k and plus you have omega squared. 1 by 2, see here 1 by 2 is here. That's why 1 by 2 omega squared. Qk is nothing but this. We have written Qk here. What is this one? Qk dagger. So Qk dagger. Again, this is a real quantity. So taking dagger, that will give you same value. So Qk dagger. Any doubt? Any doubt? Now, I into I squared minus 1, minus sign will go off. So you have 1 by 2. I pulled 1 by 2. Root of h bar omega by 2 multiplied by root of h bar omega by 2, that will give you h bar omega by 2. A dagger k plus A minus k. And this will be this one. Any doubt for the first expression? Second one, plus 1 by 2 omega squared, multiply these two will give you h bar by 2 omega k, ak plus A dagger minus k multiplied by ak dagger plus A minus k. So h bar omega by 2 multiplied by 2, that will give you h bar omega by 4. Taking common out, that will give you this. The remaining one will be this plus the remaining this one will be this. Any doubt? This omega squared and omega kk will cancel. You have h bar omega exists, so that's why you pulled out. This is your omega k square. There's a mistake here, omega k square. Is it okay? That one is omega k square. See here, omega k square is equal to k square plus m square. See, I have written wrongly here. This is omega k square. There's a mistake here. Okay, so omega k square. So that one will get cancelled. You have h bar omega. I can pull h bar omega by 4 out, so that will give you the remaining term. Now we are going to multiply this. We are going to multiply this. So multiplying this, that will give you A dagger k ak. A dagger k ak. Then A dagger k multiplied by this will give you this term. Multiplying A minus k, ak will give you this term. Multiplying A minus k dagger will give this term. Any doubt? Similarly, you are going to multiply ak dagger. So ak dagger plus ak a minus k, a minus k. The last one will be this multiplied by this, and this multiplied will give you these two terms. Any doubt? Okay, very simple one. Now we know that ak dagger equals a minus k. We know already. Ak dagger equals a minus k. We know already. So we are going to replace a minus k with ak dagger. So wherever you find the red line, so a minus k will be replaced by ak dagger. So ak dagger. Here also ak dagger. Here also you have ak dagger. So in the next equation we are going to replace. So we have replaced. Is it okay? See, for example, a minus k in the third term, this is replaced by ak dagger. See, I have replaced by ak dagger. Okay, now you just take these two terms and these two terms. They are similar, correct? These two terms are similar. We can write this as 2ak dagger a minus k. These two terms are similar, so we can write this as 2ak a dagger minus k a dagger k. I can pull these two out, so that will be ak dagger a minus k dagger. I am going to replace this one and this one, so this will become ak minus with a minus sign, so minus ak dagger a minus k dagger, both will, this will become 0. So both are the same term. See, this minus this will give you 0. So one, this term and this term and this term and this term will become 0. The remaining two terms are left out. Okay, 4 terms are left out. So we have now this term and this term, two terms, with this term and this term. See, they are similar terms, you can add these two. They are similar terms, you can add these two. Is it okay, or any doubt is there? Any doubt? Here we have done as just to interpret the operator, that will give minus sign. So these two terms are same. So subtract, that will give you 0. So 4 terms, that 4 terms will become 0. Remaining 4 terms you can write exactly like this. You just pull 2 out. 2 and this one will get cancelled. You have h power omega by 2. Remaining term ak dagger plus ak dagger ak. So we know already annihilation operator and rising operator with a commutator, that will give you 1, which we have learnt already in linear harmonic oscillator. A dagger equals 1. Can you remember? So here we are talking about in k space. So that's why ak dagger, which is equal to 1. So as usual, a b equals ab minus ba. So we can write this as exactly equal to 1, and ak dagger equals 1 plus ak dagger ak. So this can be replaced with 1 plus ak dagger ak. So this is as it is, exactly like this. So this plus this will give you 2 ak dagger ak. Now divide throughout by 2. I just take 2 this side. So that will give you h bar omega 1 by 2. These 2 and these 2 will cancel. You have ak dagger ak. Ak dagger ak is nothing but your number operator. N equals a dagger a, which you have learnt in linear harmonic oscillator, number operator. For every n, we have every energy value. For n equals 0, you have one value. For n equals 1, you have another value for E. For n equals 2, you have U2 value. So surely both will commute with each other. Simultaneously you can measure. Okay, for particular n, you will have particular E. Both will commute with each other. It means simultaneously you can measure. So n and energy Hamiltonian. So your h equals h bar omega nk plus 1 by 2, where nk is a number operator which is given by 0, 1, 2, infinity. For n equals 0, you will have h bar omega by 2, 0 point energy. This expression stands for the energy of the photon. We have quantized the field. Earlier we have quantized the field. And in quantum mechanics 1, we have quantized the particle, mechanical particle. And we have obtained the energy of the atom, 0 point energy of the atom. Even at 0 Kelvin, there exists some energy. Okay. So similarly here also, energy of the photon, we have computed energy of the photon. We have quantized the field by means of field operators, and we have obtained the expression for the quantized energy of the photon. Look over here, when nk becomes 0, we have one particular value. When nk equals 1, we have another value. Nk equals 2, we have another value. So we have quantized energy of the photon. Is it okay? Simple expression. So where nk is the number operator. Now these are the conclusions. The term in which the eigenvalue of nk equals 0 corresponds to the 0 point energy. So there exists 0 point energy. It is noted that this vacuum energy, when summed over all case, okay, all case will produce infinite value. Summed over all k will produce infinite value. So this is called a diversion. Hence, along with the scalar field, a companion spin minus half fermion field must be there. So these are all minus plus exist. So fermion field exists. So after the quantization, one finds a 0 point energy of the fermion, which is same as that in the scalar case but opposite side. Okay, hence a scalar field and the fermion occur symmetrically, which you already learned for fermions earlier. Okay, so what is the eigenvalue equation? Eigenvalue equation is given by, for the number operator, is given by number operator operates on the eigenket. Okay, eigenket which is equal to number with a eigenket. So these are all eigenkets. They live in Fock space. They are all creation annihilation operators. So Fock space they live in, not in Hilbert space. Okay, they live in Fock space. As I said, they commute with each other. Nk with H, they will commute with each other, which is equal to 0. So thus the infinite number of states, Nk1, Nk2, all eigenstates, ket states, for all possible values 0, 1, 2, infinity, for n case generate a Hilbert space. Thus the particle states obtained after quantization characterize state in the Hilbert space, and this space is known as Fock space. Okay, they are called the occupation number of number space of the particle. It implies that the Hamiltonian for the field is similar to the sum of an infinite number of harmonic oscillators, which Planck predicted, which Planck introduced the word harmonic oscillator of the ordinary quantum mechanics. Hence, the quantization of the field is equal to the quantization of harmonic oscillators. So we have quantized the field operator and we have obtained the quantized energy. Quantization of harmonic oscillators. Energies are nothing but photon energies are nothing but harmonic oscillators. Hence, the field momentum becomes, after quantization, a momentum for infinite number of particle states. So this is the conclusion which we have learned so far. In summary, the quantization procedure for the simple field is to introduce an annihilation operator and its conjugate creation operator. So you have creation operator and annihilation operator for each wave number, for each k, and integrate over them. We have done integrate over them to get Hamiltonian. Thus the Hamiltonian is then quantized as a function of ladder operators. So these are all called ladder operators. So we have rising operators, lowering operators, creation operators and annihilation operators called ladder operators. So this is the idea behind the field quantization of the real scalar field. Okay, so any doubt on the slide? So we started with field operators, field functions, which depends on position and time, and for the simplicity we have removed t we have considered as t equals 0. So your field function depends only on the position. Then we added the momentum operator. So we have field functions. One is field operators, one is your field function, another one is momentum. Okay, so phi and pi. Then we have converted this one into qk and pk. Qk and pk are ordinary coordinates and momentum coordinates in k space. Then qk and pk, they are related with ladder operators. Okay, ak, dagger and ak. So they are all ladder operators, annihilation operator and creation operators in k space. Then we have substituted the corresponding expressions for your field functions in Klein-Gordon equation. Okay, then after that we are able to get the energy of the photon, quantized energy of the photon, which is nothing but h bar omega n plus half, where n stands for number operator. Okay, so thus we have quantized the field function, field operators, and thereby we are able to get the quantized energy of the photon. So that is n. We will see in the next class. Okay, bye students.